We're now going to talk about valence electrons and non-valence electrons, which are known as core electrons. And so one question that you might have been asking yourself this whole time that we've been looking at electron configurations is, what is the point? And the point of electron configurations is they can give us insights as to how a given atom or how a given element is likely to react with other atoms. And so just to make that point or make it a little bit clearer, let's look at the electron configuration of an element that we'll see a lot of in chemistry, of oxygen. So oxygen's electron configuration is what? Pause this video and see if you can work through that. Well, in a neutral oxygen atom, you have 8 protons and 8 electrons. So first you're going to fill the one shell. Then you are going to start filling the second shell. So you're going to go 2s2. So I have 4 right now. I have to have 4 more. So then you're going to have 2p4. And notice, if I add up all of the electrons here, I have exactly 8 electrons. Now, if I'm thinking about how might oxygen react, it's interesting to look at the outer oxygen electrons, the electrons that are in the outermost shell. So the outermost shell is being described right over here, this second shell. So how many electrons are in the outermost shell? You have 6 electrons here. So oxygen has 6 valence electrons. And how many core electrons does it have? And the core electrons generally aren't reactive or aren't involved as much in reactions. It has 2 core electrons. Now, why is 6 valence electrons interesting? Well, atoms tend to be more stable when they have a filled outer shell, or in most examples, at least filled s and p subshells in their outer shell. And so in this situation, you say, okay, oxygen has 6 valence electrons, and oftentimes that's drawn with a Lewis structure, and it might look something like this, where oxygen has 1, 2, 3, 4, 5, 6 valence electrons. And you might say, hey, it would be nice if oxygen somehow were able to share or get a hold of 2 more electrons, because then that outermost shell will have a full number of 8 electrons. The 2s and the 2p would be filled in. We'd have 2p6. And so you'd say, all right, well, maybe they can grab those electrons from something else. And that's actually what oxygen does a lot of. It grabs electrons from other things. You could look at something like calcium. Pause this video. Think about what the electron configuration of calcium is, and then think about how calcium is likely to react, given that atoms tend to be more stable when they have a full outer shell, where both their s and p subshells are completely filled. Well, calcium's electron configuration, I could do it in noble gas notation or configuration. It would have the electron configuration of argon. And one of the reasons why the noble gases are so stable is that they have a completely full shell. Argon, for example, has a completely full first shell, second shell, and third shell. And then to build calcium, we'll then have 2 electrons in that 4th shell. So it is argon and then 4s2. So how many valence electrons does calcium have? Well, you can see it right over there. It has 2 valence electrons. What about its core electrons? Well, a neutral calcium atom would have 20 electrons because it has 20 protons. So it would have 18 core electrons that are less likely to react. And so you could say, what's the easiest way for calcium to get to a full outer shell? Well, instead of trying to gain 6 electrons, it might be a lot easier to just lose these 2 electrons. And it is actually the case that many times calcium will lose electrons and become ionized, will get a positive charge. So the big picture here is, one of the values of electron configuration is to think about which of your electrons are most likely to react. Those are your valence electrons. In most cases, your valence electrons are going to be your outermost electrons. They're going to be the electrons in that outermost shell. Generally speaking, if you're talking about elements that are in the s block or the p block, you can think about how many valence electrons they have just based on what column they're in. This column right over here has 1 valence electron. This column over here has 2 valence electrons. This column out here has 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons and 7 valence electrons. The noble gases here, they are very unreactive. So one way to think about it is they are very, very, very stable. They have filled their outer shell.